this video, we're going to talk about the real number line, also known as the real line for short. It's an object which organizes the system of real numbers and which is at once familiar, I imagine you've been looking at the real number line since you were in elementary school, and mysterious. Choosing a point on the real number line, like this point here, might lead us to identify it with the real number 0. Moving one unit to the right gives us the number 1, and another unit to the right, the number 2, and so on and so forth. Moving to the left of 0 lands us in the realm of negative numbers. And in between the numbers indicated on the line so far, which are integers, there also lurk fractions, rational numbers, numbers like 2/3 or minus 3/2. There are stranger beasts on the real line than even that. Consider the irrational number square root of 2, which is approximately here, or another famous irrational number, pi, which is just to the right of 3. All of these numbers are organized into one structure, which we refer to as the real line. And it's a structure on which a great deal of mathematics takes place. Though you've likely been working with number lines for a long time, I'd like to underscore the fact that the real line is indeed a very complicated structure, and it's easy to ask simple questions about the real number line that turn out to be very difficult to answer. Consider, for instance, the question, what is a real number? Or the question, how many real numbers are there exactly? Or the question, does the real line have any gaps or holes in it? So, for example, if it appears to be the case that a certain curve intersects the real line, how can you be sure that it actually does? How can you be sure that after zooming in on the supposed point of intersection, you don't actually discover a gap through which the curve passes? Again, although these questions might sound simple, there's actually a lot of very advanced mathematics that lurks behind them. So it's good to approach the real line with a little bit of humility. The real line has a natural ordering on it, which simply means that if we take any two numbers on the real line, let's call them A and B, it's always possible to compare them. It's always possible to say that one of them is less than or equal to the other. This ordering, in turn, allows us to define some nice subsets of the real line, which are known as intervals, and which you'll encounter again and again in math class. A basic example of an interval is a so-called open interval, which is defined using fancy-looking set-theoretic notation here. It's denoted using parentheses, and the open interval from A to B is simply, let's pick this apart, the set of all real numbers x, and this notation means all x that belong to the set of real numbers, denoted by this funny-looking r, such that x is greater than A and less than B. Likewise, a closed interval is defined using square brackets, and the closed interval from A to B is the set of all real numbers x, such that x is greater than or equal to A and less than or equal to B. So the difference between a closed interval and an open one is that a closed interval includes the two endpoints A and B. By playing around with inequality symbols, we can go on to define a bunch of other kinds of intervals as well. A half-open interval, for example, is one that includes one of the endpoints, such as the left endpoint, but excludes the other endpoint, such as the right endpoint, which is the case here. So the half-open interval from A to B with a square bracket on the left and a parenthesis on the right would be the set of all real numbers x, such that x is greater than or equal to A, but strictly less than B. And here's just one more example. Some intervals can be infinite in length. and an interval of the kind shown here is often called a ray. And it consists of identifying some number a and then letting the interval go all the way out to infinity. And if we wanted to define this rigorously, we would simply say that this particular ray, which is written using parentheses, is the set of all real numbers x such that x is strictly greater than a. Now, intervals are sets. They're sets of real numbers, and as such, we can perform set-theoretic operations on them. One fundamental such operation is the union of sets. So given two sets, that is to say, two collections of objects, be they numbers or names or anything else, called A and B, which are depicted here via two circles, the union of A and B works as follows. It's denoted using the union symbol, which resembles the letter U, and it's defined, and it's important to be careful about the language here, to be the set of all elements that belong to A or that belong to the set B. And in our diagram, our Venn diagram here, this would consist of everything that's been shaded in green. Once again, we want to consider everything in A or everything in B. All the elements, in other words, in both sets taken together. Likewise, we can talk about the intersection of two sets, which is denoted using a special intersection symbol, which looks just like the union symbol, but flipped upside down. And the intersection is defined, and it's once again important to be careful about the language, as the set of all elements in A and in B. So looking at our Venn diagram, the intersection consists only of the portion of the two sets that overlap. Only, once again, the set of all elements that are both in A and in the set B. Let's take a look at a couple examples that ask us to think about the union or the intersection of two intervals on the real line. This first example is asking us to think about the union of the open interval from 0 to 4 and the half-open interval from 2 to 7, where this half-open interval is open on the left but closed on the right. To get a feeling for what's going on, it can be helpful to mark or indicate both intervals on the real line. So the open interval from 0 to 4, we might sort of indicate with a set of open parentheses like this, keeping in mind that the interval itself consists of everything that is strictly in between 0 and 4. And likewise, the half-open interval from 2 to 7, we might denote in a similar fashion. Let me use a different color for it. It would be everything that is strictly greater than 2 and less than or equal to 7. And we want to keep in mind here that the union of our two intervals is going to be everything that's in the first interval or in the second. In other words, it's going to be all the numbers in both intervals taken together. Once we realize that, it's easy to rewrite our original union of intervals in a more meaningful form as the half-open interval from 0 to 7, with a parentheses on the left and a square bracket on the right. Here's a second example that involves an intersection, specifically the intersection of the closed interval from -3 to 1 with the open interval from 0 to 8. Let's think about how to compute that. So let's take a look. The closed interval from -3 to 1 is the set of all numbers in between and including -3 and 1. So it consists of truly everything that's highlighted in yellow here. And the open interval from 0 to 8 would look basically like this. It is everything that is strictly greater than 0 and strictly less than the number 8. And when considering the intersection of these two intervals, what we want to do is consider the set of all numbers that belong to the closed interval from 3 to 1 and the open interval from 0 to 8. And a bit of thought shows that this is going to just consist of this piece where the two intervals overlap. In other words, the intersection that we want can be written simply as the half-open interval from 0 to 1, with a parentheses on the left and a square bracket on the right.